Alright, we're going to talk a little bit more about linear regression first, and then we'll get into what happens if the data is not linear. So, a couple more things. The least squares regression line is what we call that line of best fit. So the line we get when we run a linear regression analysis is called the least squares regression line. And the reason it's called that is because of this first little fact, that it's the line that minimizes the sum of the squared residuals. So when I have a set of data and I have a bunch of points, and I have a line that goes through them. Remember, a residual is that distance between the line and the point. So that vertical distance between the line and the point is a residual. So what this means is that if we were to take all of those distances and square them, this is the line that has the least possible value for that sum of the squared residuals. And that is why it is called the least squares regression line. That's where that word or that name comes from, is that fact that when we take all of those residual distances and square them, we want the least possible value. So this is true, but it's also true that this is the line for which the sum of all the residuals is 0. So if I were to just take all the residuals themselves without squaring them and add them together, I should get 0. Remember, some of our residuals are positive, some are negative. We add them all together, we're going to get 0. And then it also is true that this line goes through the point x bar, y bar. So mean of the x's, mean of the y's. We know that our line will go through that point. And that's actually the first part of how we could potentially write the equation of that line given some specific data. So there's the mean of the x's. This is the mother's age, father's age data. So the mean of the x's or the mean of the mother's age is right here. And then the mean of the father's age, the y bar, is right there. So we know that our line has to go through that kind of point in the middle where x bar and y bar meet. So we know it goes through there, but in terms of its slope, well, that slope is dependent upon a few things, one of them being the correlation value. So how strong that correlation value is going to help determine like how steep or not steep that line is, but also it has to do with the standard deviations of each of those values. So we're going to take that equation and actually answer some questions. If we know the correlation and the means and standard deviations of both x and y, if we knew that information, we could actually use that information to calculate our equation. So we're going to practice doing that. This is data, or this is information that's on your formula chart that you will get at some point. But these two things are on it, and I'll make sure to point them out to you. But if we had this information, and sometimes we're given it to it just like this, where we have all the information in a nice little table, but we may also be given this information in words, so you just have to read carefully. So I'm going to start by finding the slope. So the slope, which we call b, is going to be your correlation times standard deviation of y divided by standard deviation of x. So I always like to think of it as, you know, it's rise over run still, so y is always on top and x is always on bottom. So my correlation for this set of data was 0.5, so pretty weak correlation. Standard deviation of y is 3, divided by standard deviation of x is 2. So I have 0.5 times 3/2, which is 0.75. So that's our slope, so we know that. Now in terms of actually getting our equation, so now that we know the slope, we can use that fact that we know this line is going to go through the line x bar, y bar. So we can actually use that to kind of come up with the y-intercept. So if I know that my equation is going to be y, or predicted y, equals a plus bx, and I now know that b is 0.75, I can use a point that I have on the graph. I know that it goes through the point 10, 20. I can use that to figure out what my y-intercept is. So I'm going to plug in 20 for y, and I'm going to plug in 10 for x. I'm going to do a little math, so solving, doing some algebra. 12.5. So now I know that my y-intercept is 12.5. I know that my slope is 0.75, so now I can write my equation. Y equals, or y hat equals 12.5 plus 0.75 times x. So now I have my linear regression equation. This is one where there was no context. We didn't know what these variables represented, so it's okay to leave it like this. As always, if you're dealing with a problem where you do know the variables and what they represent, we would want to put this in context. So put the actual variable names instead of just leaving it as y and